Welcome to the CHI webinar. My name is Karen, and today's topic is integrated 1D-2D modeling using PCSWM. In many cases, the modeling of overland flood flow in a strictly 1D solution can be problematic, as there can be numerous flow paths around various obstructions. 2D modeling is a powerful tool that allows the user to account for these numerous flow paths and as well allows them to create visually impressive flood maps and animations. So for today's webinar, I'm going to begin by talking about some of the theory behind PCSWM 2D. From there, I'll be moving on to talk about some of the benchmarking tests we completed as part of our validation effort, and I'll be ending today with a case study and demonstration. Now let's get started. Okay, so a little bit about the history of SWM5's dynamic wave routing. It started in 1965 with Bob Shabinsky, who created the dynamic estuary model. From there, in 1971, Larry Rossner took over with SWM Receive. In 1988, Larry Rossner developed SWM4 Extran, and in 2005, Lou Rossman took over and created the SWM5 dynamic wave routing model, which is what we use now, and it's used in PCSWM. What a lot of people don't realize about the dynamic estuary model was it was intended to be a 2D model. However, due to computational limitations, this was probably the largest 2D model they could develop at that particular time. So to use our approach to 2D modeling, we do have a few assumptions. The first one is that the flow between cells is predominantly one-dimensional. The flow between cells can be represented with rectangular cross-sections, so that will make a bit more sense in a minute. The Coriolis and wind effects are negligible, and the wavelength is significantly greater than the depth, so we can use the shallow water equations or the St. Bennett equations. The applications for 2D modeling include urban and watershed flood modeling, where flood sources include distributed rainfall, riverbank overtopping, and flooding sewers, such as a major and minor system or a dual drainage system, where you have your roadway conveyance going into your minor system or your pipes underground. So for those of you who are a visual learner, I think you'll really like PCSWM 2D. It's a very visual software. It's very colorful. You can see right away where the areas of concern will be, and you can animate it. So it is very user-friendly, and it is very appealing on the eyes. Okay, so how PCSWM represents the storage on the fields or on your flood area is using rectangular conduit with a length and a width value automatically assigned. So PCSWM adjusts the length and the width of the conduits according to a specific ratio, dependent on the number of links that are connected to the node. This ratio was determined using a series of benchmarking tests that I'll be talking about in the next presentation. Essentially, the length to width ratio for those rectangular conduits is equal to 0.2 times the number of connected conduits. So in the example we're looking at here, n would equal 6 because there's 6 connecting conduits on each 2D node. So here's one application of integrated 1D-2D modeling, and that would be riverbank overtopping. So in the first picture on the left here, you see the dashed line going through the river conduit. So the transect you can see on the top right, that's supposed to be the location of that dashed line on the river. You can see the regular 1D approach. You generally have your main channel, and from there you'd have your overbanks defined to represent the full cross-section. If you were to use a 2D approach, what you'd want to do is truncate or remove the overbank portion of your model and just have the main channel modeled in 1D, and the overbanks represented using a 2D overland mesh. The second application is a dual drainage application or major-minor system, where you have your major system conveyance and your minor system conveyance, and they're linked. You can do this in PCSWM 2D. Instead of representing your major system in 1D, you'd represent your 2D flood area using your 2D overland mesh, and then you'd connect that to your 1D network or your minor system. You can have connections represented as orifices for catch basins, or you could use direct connections for shared bridges or shared nodes, such as in the case of bridges or culverts. So what we're looking at here is a DEM, or a digital elevation model. This particular digital elevation model came from California Delta. It's actually a very high resolution DEM, and normally, or a lot of times, when you have a river channel like this, the surface water elevation is what's sampled in the DEM. However, in this case, the LiDAR was able to capture the river bathymetry, so there's no need to have a 1D component of the model representing the channel. below that water surface elevation. So in this case, we're going to model the whole area using exclusively 2D. So I'm just going to quickly go through the steps involved in creating a 2D model. The first step is to create a bounding polygon layer. So the bounding polygon layer is essentially where you want to have that 2D model or the 2D overland mesh. In this example, we've specified two different areas. The first one is the river channel area, and the second one is just the general fields layer around that river channel. Now in this case, because we have a river channel running through our study area, we can use something called the directional mesh. Directional mesh is essentially a rectangular mesh that follows a center line, so the 2D cells are drawn perpendicular to that center line. The advantage to this is that your 2D mesh can follow the natural flow of that river channel, if it's known, and it also keeps your model smaller. So by using a rectangular mesh, there's actually only 4 conduits drawn per 2D node, as opposed to 6 with a hexagonal mesh. The next step is to generate our 2D nodes. The 2D nodes sample the DEM elevation, and then from there that elevation will be taken and assigned as the bottom average elevation for the 2D cells. Now you can see there's areas where the resolution of the 2D nodes is greater than other areas, and that's just because we use an adaptive mesh, which allows you to specify a distance tolerance and an elevation tolerance. So the areas that are flatter have a coarser resolution, and the areas where the topography changes, you have a higher resolution of sampling points to capture those changes in your landscape. From there, you can create your 2D mesh. This is looking at your 2D cells, and then you can see your 2D mesh. And here I've just rendered our 2D cells on the elevation that each of the cells were assigned. So you can clearly see where the river is. It's quite a bit deeper than the rest of the area around it. And this is just zoomed out. This was a fairly big model. And after we ran the model, you can obviously render the 2D cells based on their maximum depths. So this study was actually part of a floodplain reconnection study. And this was to try to rehabilitate some of the previously existing wetlands for juvenile Chinook salmon. The study was located in the California Delta, close to Sacramento. This picture is basically showing juvenile Chinook salmon. They are the same age. The only difference is that the ones on the left were raised in fast-moving stream, so there wasn't a lot of hiding spots, there was more predators, and there wasn't the food source and nutrient source that there would be on the Chinook salmon that are on the right that were raised in a floodplain area where there was more hiding spots, greater access to nutrients, and just a better environment for the juvenile Chinook salmon to grow to their full potential. So ultimately the study was to see if by reconnecting the floodplain, we were able to have a long enough duration of the flood flow on the floodplains to be able to raise these juvenile Chinook salmon into maturity. So in order to do this, there was an existing levee, and the idea was that the levee would be removed to create this floodplain area. We went in the DEM and we actually removed that levee from the DEM. And here's a video. Again, one thing I like about PCSWM 2D is it is a very visual program. So after you create your model and run it, you can actually animate your results and see what happened. So I'm going to click play on this. So you can see now how the flood flows spread into the surrounding fields, creating that flooding area. And what we're interested in is the number of days that those floodwaters are on those fields, to see if it's long enough for those Chinook salmon to reach maturity. So once we ran the simulation, we were able to do an area duration frequency analysis to determine if the duration of time the flood flows were on the fields were sufficient for the Chinook salmon to reach maturity. So just as a recap, some applications include integrated 1D-2D modeling of watersheds for river-based flood analysis, integrated 1D-2D modeling of stream flooding for urban areas, and integrated 1D-2D modeling of major and minor systems or dual drainage systems. Some advantages are that you can have a fully integrated solution, so you can seamlessly move between 1D and 2D. I'll talk a bit more about that when I get to my demonstration. You can include water quality modeling. You can have real-time control, and you can also have distributed hydrology. So I'm going to be moving on to talk a little bit about the benchmarking tests that were used to verify PCSWM-2D and its performance. These benchmarking tests were obtained from the Environment Agency in the UK, and they were from a report called Delivering Benefits Through Evidence, benchmarking the latest generation of 2D hydraulic modeling packages. Now, the objective of these benchmarking tests were to provide evidence to ensure that these 2D models were capable of adequately predicting the variables upon which flood risk management decisions are based. So basically, are they usable and can we trust their answers? Just a quick overview, there was 10 tests in total. Test 6 and Test 8 both had 2 components, so I will be talking about some of those tests right now. So the first test was called Flooding a Disconnected Water Body, and the objective was to assess the basic capabilities such as handling disconnected water bodies and wetting and drying floodplains. In the screenshot, we have a profile of the DEM that was used for Test 1, and you can see on the left-hand side an inflow hydrograph was introduced at that location. Ultimately, we were interested in knowing what the time series were for the water surface elevations for point 1 and point 2. So a varying water level hydrograph was introduced along the dashed red line you can see in the first screenshot. All other boundaries were closed, and there was an initial condition that the water level was 9.7 meters at the beginning of the simulation. And this was the inflow hydrograph. It was a water level hydrograph, and you can see how it changes from 9.7 meters to 10.35 meters, and then back down to 9.7 meters. And this is what the mesh looked like. If you see on the left-hand side, you can see we used outfalls to introduce the inflow hydrograph, and that's because it was a water level hydrograph as opposed to a flow hydrograph. Now for this particular test, the Manning's roughness was 0.03, the grid resolution was 10 meters, and the simulation time was 20 hours. Now for all these tests we had to do for the benchmarking tests, all these parameters were already preset for us, so we just had to make the model using their parameters already outlined. So you'll be seeing quite a few of these plots. In all cases, PCSWM will be shown in the yellow dots. In this case, we're looking at the water level for point 1, and this is the water level for point 2. And you can see in both cases we did very well. Moving on to test 2, it's called Filling of Floodplain Depressions. The objective was to assess the package's ability to handle disconnected water bodies with an emphasis on the final distribution rather than the peaks. In this particular DEM, there was an underlying slope of 0.001 west to east and north to south. In this particular case, the inflow was introduced at the small red line you can see in the screenshot there, and all other boundaries were closed, and there was an initial condition of a dry bed. And this is what the inflow hydrograph looked like, which was provided. And this is what our final mesh looked like. So we had a Manning's roughness of 0.03, a grid resolution of 20 meters, and a simulation time of 48 hours. And again, I like PCSWM-2D a lot just because you can make really nice animations. So I'm just going to let this video run. And ultimately, you get a good idea of what the final distribution of the water was when you have this sort of animation. So these are the results from test 2, starting at point 4. You can see in the little schematic I have beside the legend what location we're looking at in the DEM. Point 3, point 2, point 1, point 8, 7, 6, 5, 12, and in all these cases we're doing very well. Moving on to test 3, it's called Momentum Conservation over a Small Obstruction. The objective was to assess Swim 5 or PCSWM's ability to conserve momentum over an obstruction. So you can see, like in all of the tests, the inflow hydrograph was introduced on the left-hand side of the DEM, and we're interested in the water surface elevations for point 1 and point 2. This is looking down onto the DEM. Again, the inflow boundary condition is on the left-hand side. And this was the inflow hydrograph we used. This is what the mesh looked like. We used a Manning's roughness of 0.01, a grid resolution of 5 meters, and a simulation time of 15 minutes. So in this case, although there are oscillations in our results, a lot of the other software packages also seem to have those oscillations, and we have a water level of approximately between 9.95 and 10 meters. So we're fairly happy with our results. We seem to be really consistent with the other software packages. Test 4 was titled Flood Propagation over an Extended Floodplain. The objective was to assess the package's ability to simulate the celerity and propagation of a flood wave and predict transient velocities and depths. So this test was relevant to fluvial and coastal inundation resulting from breached embankments. Now what was interesting about this test is that there was no DEM provided, so we used a uniform elevation of 0 meters. In this test, the inflow bounding condition was applied along a 20-meter line in the middle of the western side of the floodplain, so basically on the left-hand side in the center there, close to point 1. And all other boundaries were closed, and there was an initial condition of a dry bed. And this is what the inflow hydrograph looked like. And this was a fairly large model, almost 100,000 cells. Now you wouldn't want to go any further than that, as you may experience memory problems or long computational run times. The Manning's roughness value we used was 0.05. We had a grid resolution of 5 meters and a simulation time of 5 hours. I'm just going to quickly go through the results. 0.1, 0.3, again we did very well. 0.5, 0.6, and this is looking at the depths of water at the cross-section of time equals 1 hour. Okay, moving on to test 5. Test 5 was more of a valley scale model. It was an actual DEM from an undisclosed location, and the objective was to assess the ability to simulate major flood inundation at the valley scale. And I have a second screenshot there showing the profile of the elevations along that channel, shown in the dashed green line on the DEM there in that figure on the right. So the specifications were that an inflow hydrograph was introduced along the small black line at the bottom of that DEM, and all other boundaries were closed. This was a hydrograph, or the inflow hydrograph, that was used, and it represented a typical failure of a small clay embankment dam. And they wanted to use the particular DEM they did because they wanted to ensure that both supercritical and subcritical flows would occur in different parts of that field. Some of the mesh parameter values: the Manning's roughness was 0.04, the grid resolution was 50 meters, and there was a simulation time of 30 hours. Now this was the first test that we used a directional mesh in, and you can see in the screenshot how the mesh follows the contours of the river segment. So there were predicted results provided from the Environment Agency. And again, I really like videos, so this one is actually showing the cells rendered based on their velocity values. Okay, quickly going through the results. This is looking at 0.1, 0.3, 0.5, 0.7. Again, we're doing very well. There were some additional plots we had to put together, and these are the results of cross-section of peak levels along the valley center line. So in this particular image, the green thick line represents the DEM elevation, and the other lines represent the results from the other software packages. Again, PCSWMM is shown in the yellow dots, and this is showing the peak elevations at that location. And this is between the 2 kilometer and 5 kilometer mark, shown in the little schematic on the right there. Okay, test 7. Test 7 was called River and Floodplain Linking, and the objective was to assess the ability to simulate fluvial flooding in a relatively large river with floodplain flooding taking place as a result of riverbank overtopping. Now you can see in the picture on the right-hand side that there's stars with M numbers. So for example, the top M number is M013. Those are representing cross-sections that they provided. So how this test was to be set up was to have the center channel modeled in 1D and then connect that center channel to 3 floodplains. In the figure shown in this slide, you can see on the right-hand side in blue, those polygons represent the 3 floodplains that we had to connect or link that 1D channel to. There was an initial condition of a uniform water level of 9.8 meters. We had two Manning's roughness values provided. The first one was for the 1D portion, or the center part of that floodplain area, and that value was 0.028. And then we had to use a value of 0.04 for the three floodplains you can see there. There was a grid resolution of 20 meters, and the simulation time was 72 hours. The model inventory comprised of approximately 20,000 2D cells and 20,000 nodes. Now I'm going to go through each floodplain because in this particular test it had a lot of interesting features that presented some challenges, and I want to talk a little bit about how we overcame each one. So this is the first floodplain. Starting with the blue arrow located at the bottom of the screen here, that's representing an opening in the embankment. So what we had to do there is somehow connect that floodplain back to the 1D channel, and I'll talk a little bit about how we did that in a minute. Now there's also the black X's you can see along the bank, or crosses. What those are representing as the location we had to connect the floodplain to the 1D channel. We have the purple circles, those are the sample points. In this particular case, we're looking at the elevations, or the water surface elevations over time. And then we have the black dots on the very top, which represent a berm that we had to represent in the model. And then we were given the black line as the outer extent of the model. So that's what we used for the bounding polygon. So this is looking at floodplain 1. You can see in red, I have the boundary polygon defined. The red crosses with the numbers, those represent the sample points. And of course the X's are where we had to connect the 1D portion of the model to the 2D overland mesh. This is looking at our 2D nodes layer. So again, the resolution was 20 meters. These are the 2D cells rendered according to their elevations. Now one of the challenges we faced with this model was this berm and how to represent it. What happened was the resolution of the mesh was too coarse and links were being drawn that bypassed the berm. So what we had to do was go into the model and add additional 2D nodes to that section. Alternately, you could use a break line layer. It's basically a line layer that you draw, and PCSWM would ensure that it would draw the 2D nodes along that line. For more information on how to use a break line layer, I recommend you visit our website at support@chaiwater.com. And you can see here, by adding those additional 2D points, we were able to capture that berm, so there were no links bypassing that berm. So here's that sluice gate we had to draw. This is linking the bottom of floodplain 1 to the main channel. And for that particular connection, we used an open rectangular conduit. And because of the integrated 1D-2D component of PCSWM 2D, you can view, in this case I'm looking at profile going from our 2D overland mesh through my sluice and back into my 1D model. Moving on to floodplain 2, again, purple dots represent the sample points. The hollow black dots represent berms or interesting structures or features that had to be taken into account and represented. And the little X's are where we had to connect the floodplain 2 to the 1D component of the model. So this is looking at the boundary of floodplain 2, and then the 2D nodes. And these are the 2D cells rendered based on their elevations. And again, these little features were very significant in representing the model correctly. In this particular case, we just added additional 2D nodes prior to creating the mesh. However, you could have used a break line layer to represent those areas as well. And these are the 2D cells rendered according to their assigned elevations. And you can see we've managed to capture those little features. And I believe in this case, they're actually an elevated roadway. And moving on to floodplain 3, again, the purple dots are the sample points. In this particular case, there was something called an Upton Island. There was a little island in the middle of the floodplain. We also had a bridge, a culvert, a pool brick culvert, and a few other little features represented in the black circles that had to be taken into account. So this is looking at the boundary for floodplain 3. This is looking at the 2D nodes. And then the 2D cells rendered based on their assigned elevation. And you can see we were able to capture that Upton Island using the 20-meter resolution. We did have to include a pool brook culvert which was added directly from the 1D mesh to the 2D mesh. And again, you can easily see the profiles going from the 1D component of the model to the 2D overland mesh. There was another feature, this is actually looking at a bridge that we had to represent. Using the resolution of 20 meters, there were some links originally drawn that bypassed those features that would obstruct the flow. So we actually went in and we added additional points. Again, you could have used a brake line layer, and you can see that elevations were captured. We also had to add a small bridge to this particular model as well, which was really easy to do just by adding a culvert there. And it was representing this bridge here. And again, you can go directly from the 2D component of the model to 1D component, which is that bridge we added, back to the 2D component. And we did have another feature here. I believe this is another highway. And we just added additional points to that location. And you can see it was captured nicely by this mesh. As for the connections, because the boundary polygon wasn't over top of the 1D portion of the model, we weren't able to use the connecting tool to create those connections. So there was a pool brook culvert, like I mentioned, and this was just added to the model by adding a culvert and connecting it directly from the 1D component to that floodplain 3. And you can see you can easily transition between the 1D portion of the model to the 2D portion of the model, and you can view the profile and animate the profile using PCSWM 2D. Now again, there was some interesting features that were important to be captured. By taking the strategy of adding additional 2D nodes, we were able to capture those elevations along that, in that case, bridge. This was the bridge that we're representing in that location. Again, it was very easy to add that 1D section of the model, and you can transition between one and the other flawlessly. This was looking at an elevated road in that particular floodplain, and again, it was very important we captured that using additional 2D points. As for the connections were made manually using side orifices. Normally, you'd be able to use the Connect 1D to 2D tool available in PCSWM. However, in order to use that, the bounding polygon has to be over top of the 1D model, where in this case, the floodplains were modeled separately, so we had to make those connections directly. What we did is we used orifices where the width was equal to half of the upstream length plus half of the downstream length, and the offset was the 2D invert elevation minus the 1D invert elevation. And that strategy seemed to work really well. Now we were given two boundary conditions, given an upstream boundary condition and a downstream boundary condition. The upstream boundary condition was an inflow versus time, and that was applied at the northernmost cross section. In the 1D model, it was introduced at the very top of the model on that first cross section M013. The downstream boundary condition, there was a downstream rating curve provided, of flow versus head, and that was applied at the southernmost cross section in the model, so that 1D cross section titled M054. So I'm going to quickly go through the results. In this case, we did very well. So this is looking at point 1, point 2, point 6, point 8, point 9, point 11, point 12. Again, we did very well for all these tests. You'll also notice there weren't as many packages who submitted results for these latter tests, as the integrated 1D 2D component is not available for all the software packages that were tested. Point 17, and so on. So the last test I'll be going over is test 8A, which tests the capability to simulate shallow flows in urban areas from inputs from rainfall. So the modeled area was approximately 0.4 kilometers by 0.96 kilometers, and the project covered the entire DEM. And in this particular case, the flood was assumed to arise from two sources. The first one was a uniformly distributed rainfall event, and the second one was from a point source location representing a surcharging culvert. So you can see where that inflow arrow is pointing to that dot there. Here are those two different boundary conditions. So the first one was that distributed rainfall, and you can see it's a very simple hydrograph with uniform intensity of 400 millimeters per hour. And then we have that inflow discharge there which has a peak discharge of about 5 cubic meters per second. For test 8, we used an adaptive mesh, where the Manning's roughness was 0.02 for the roadways and 0.05 everywhere else. The grid resolution was 2 meters, and the simulation time was about 5 hours. And I'm just going to quickly go over the results. You can see we did very well in these as well. So in conclusion, in all tested scenarios, pressure, friction, and slope were the dominant terms, and a well-constructed 3-term model such as PCSWM can provide more consistent results than the group of tested 4-term models. And we found that other factors, such as those elevated roadways and features in the DEM, have more of a significant impact on the model results. So CHI would just like to thank the Environment Agency in the UK for supplying the data sets. So I'm going to be moving on to the demonstration portion of today's webinar. The purpose of the demonstration is to introduce you into some of the 2D tools and the 2D interface, and also show you how to set up a simple 2D model. So the project we're going to be working with today is called Sears Point Restoration Project, and it's part of a large wetland restoration and enhancement effort being undertaken by the Sonoma Land Trust on San Paulo Bay north of San Francisco. So let's get started. So what we're looking at now is the Sears Point 1D model. Now the ultimate goal of this model was to determine the required capacity of 2 new pumps. The criteria for determining the pump capacity included the prevention of flooding Highway 37 and providing reasonable drawdown times for water ponding on the fields south of the highway. Now while working on this project, it was observed that the 1D ditches used to convey the stormwater were shallow and had a tendency to overtop onto the surrounding fields. Originally, storage units were used to represent the ponding on the fields. However, the size of the storage units and the drawdown values were difficult to measure. In this case, we found that using a 2D overland mesh better represented the storage on the fields, and we could actually measure the drawdown time without the use of storage units. So I'm going to go over how to create that 2D overland mesh, and then from there link it to the 1D portion of the model. Okay, so to begin with, I'm going to click on the File tab to open the Backstage, and I'm going to select 2D. I'm going to toggle on Enable 2D Modeling. Now in order to save time, I've already created a bounding layer. So bounding layer is basically a polygon that specifies which area you want your 2D mesh in. Since I've already created it, I can just click on the Open button and open that bounding polygon. Now the 2D nodes layer is basically a points layer that will sample the DEM, or the digital elevation model, and extract the elevations and assign it to an attribute in those points. I will create a new layer for the 2D nodes. And the last layer I'll need for this model is the DEM layer. And PCSWM has already recognized I have a DEM in the model, so it's already selected it in the drop-down layer. If you are interested in what these other layers are, I recommend you go through our 2D documentation available from support@chiwater.com. Okay, so now I have my bounding polygons shown in red. So the first step is to parameterize, or to assign the attributes that you want associated with your 2D mesh. So the first thing I'm going to do is I'm going to select my bounding polygon, and I'm going to unlock it. And then I'm going to select all the objects in that layer. So there's actually only 2 polygons in that layer, so I will select them both. And now I can select, or I can parameterize my mesh. So in this case, I have a few options into what style of mesh I want. There's hexagonal, rectangular, directional, and adaptive. I'm not going to go through what the difference between each one is. However, we do have, again, support documentation available on our website, and I recommend you go visit that to see the differences between each one. Now in this example, I'm going to use a hexagonal mesh, as it will give the most degrees of freedom for the water onto the floodplain or fields. This is the resolution of our 2D overland mesh. I'm going to leave it at 150 feet. And my roughness value, that's your Manning's roughness, I will change it to 0.014. Okay, so that's actually all I need to do to parameterize my mesh. So my next step is to actually create the 2D mesh for my model. So how I do that is click on the Tools button, go to 2D Modeling, and I want to pick Generate Points. So basically the points, or the 2D nodes, are points that will sample the digital elevation model and extract that elevation, and then from there that elevation will be used to create your 2D mesh. So I'm going to click on Generate Points. Since we've already defined our 2D nodes layer, our bounding layer, and our DEM, I don't actually have to select anything here. I can just click on the OK button. Notice how PCSWM will estimate how many points this operation will create based on your parameters in your bounding polygons. Okay, so it should happen fairly quickly. I can zoom into my 2D nodes, and from there I can click on them. And you'll see that the style has been indicated as being hexagonal because we've assigned those bounding polygons to have a hexagonal mesh. And the elevation from the digital elevation model has been sampled. So actually if I scroll in and hover over the point, you'll see at the bottom of the screen what the Z elevation value is, and it should match what you have assigned to that point. Okay, so if I wanted to, say I had an area where there was sharp depression or change in your area, or if there was a feature that you wanted to capture but the points resolution you selected wasn't able to, one thing you can do is add additional points to your layer after your 2D nodes have been generated. So to do that, you just have to select the 2D nodes layer, click on the Add button, and then from there you just click on where you want those additional nodes. Once you do that, note that the style of the additional nodes you've added will be marked as being adaptive, and the elevation will be sampled on the fly. So now that I'm happy with my 2D nodes, I can now go ahead and create my 2D overland mesh. So to do that, I want to click on the Tools button and go to the next item in the workflow, which is Create Mesh. Again, PCSWM does a very good job at selecting the layers for each drop-down box. So I can just click on OK. And PCSWM will go ahead and create my 2D mesh. Once your mesh has been created, PCSWM will generate a report. You can close that. And so we can see the mesh. I'm just going to turn off our 2D nodes so we can zoom in and take a look at our mesh. So you can see the 2D portion of the model has been rendered with black links and smaller gray nodes. And you can see the 2D cell are those honeycomb polygons you see. In the areas where we added additional points, you can see how PCSWM now has adapted the mesh to account for that particular area. Okay, so now that we've generated our 2D overland mesh, the next step is to connect the 1D portion of the model to the 2D overland mesh. So to do that, we need to tell PCSWM which 1D nodes we want the 2D portion of the model to connect to. And how you do that is you add a tag to the 1D junctions saying connect 2D. And then PCSWM will go ahead and look for that tag connect 2D and connect all the junctions with that tag to the 2D overland mesh. So I've already gone ahead and indicated where I wanted PCSWM to connect to the 2D mesh, and I'll just show you where they are using the Find tool. So I'm going to find the junctions with a tag that has a value of connect 2D. I can select those. And you can see I have 71 junctions that I'm going to connect to my 2D overland mesh. Okay, so I just have to go to my tools, and I will select Connect 1D to 2D. There's two options. You can use bottom orifices, or you can connect to 1D nodes directly. I'm going to choose to connect to the 1D nodes directly and click OK. Once it's done, if you have an error, it will show your error. In this case, it's not a big deal. What happened was there happened to be two 1D nodes specified to join to the 2D overland mesh. However, it could only connect one of those 1D nodes. So that's all that's saying. It's not important. I can close that. And now let's zoom into one of the nodes that connected to the 2D overland mesh. So if we look at this particular cell, you can see prior to the connection, there was a 2D junction in the center of that cell. By indicating to PCSWM to connect the 1D portion of the model to the 2D overland mesh using a direct connection, PCSWM will remove that 2D node and from there connect all those 2D links to that 1D node within the cell. So what this now will allow me to do is select the 1D conduits and then from there go directly to the 2D portion of the model. So if I look at my profile, I should see the 1D channel would be a little bit lower than the overland mesh. So this would be the 2D component. So now that I've created my mesh and I've joined the 1D portion of the model to the 2D overland mesh, I can run my model. From there, I can animate my model and view my results. Okay, so now that our model has been run, I can thematically render the 2D cells to show the max depths of water on the field. And I can also animate this model. So you can see over time the water accumulates onto the field, and then eventually the pumps will turn on and dewater those fields. So that's an overview of integrated 1D-2D modeling using PCSWM. If you'd like to learn more about PCSWM or have any questions, feel free to visit our support site at support.chaiwater.com or send us an email to support@chaiwater.com. Thanks for watching!